it should be, yeah. Right, which screen am I sharing? Excuse me. Now, which one is my desktop one? This is my desktop too. Oh, okay. What do you see now? Because I cannot really see. You see some website?
Yes.
Oh, okay. So this is the screen I'm sharing now. Okay, so I mean, the main program I will be going through today is this program by Hemans. It's very famous in seismology, computer programs in seismology, and it's virtually helps you to do a lot of things. So I think I sent you also the link to this website. You have the documentation. Okay, so the source code, some tutorials which we'll be looking at, and some updates, some workshops, and also some dependency programs that you need to install to work for it to work smoothly. So yeah, okay. So this part of the tutorial, I don't know if you guys can install, because then it could have been nice. You guys, okay, so apart from Simone that is on Windows, I think almost all of you are on Linux, no?
I'm on Windows too.
No, guys, I think today just unmute your mic because it's just a tutorial. It's just a discussion session. It's not really me talking. Okay?
Okay.
Yeah.
I am on Windows too.
And who else?
Windows 2.
Windows 2, okay.
Sorry, what did you say? Windows 2.
No, not Windows.
What? Zoom and the other guys, why are you not, your mics are on mute still? I mean, I want to hear you guys. I said it's just a tutorial. That's what this is. It's not really just me talking. So please just unmute your mic and let's discuss.
Let's unmute your this one video too. Let's see you.
Video is not important. Why?
Okay. We didn't even ask your name, Professor.
Well, I guess okay. Sorry, I'm Daniel. Yeah. I mean, I thought it's on the website, so yeah. Okay, I'm sorry. Yeah. So yeah. So okay, none of you guys have the program installed, yeah?
No.
This is because it's really straightforward. I mean, once you, but the other guys, why are you on Windows? I thought the ICT system has the how do you call it, Linux? Okay. Anyway, so right, this is a bit confusing. Okay, so let me just bring this up and let's see. In any case. Okay, so now I see about two of you, your mics are still mute. Why? What are you scared of?
Dung.
So this.
Yeah. Don't mute your mic. Talk.
Share. Desktop. Two. Okay, so this is two now. Okay. So, okay. So today we'll be looking at the Earth structure. Like, okay, yesterday we did more of the mathematical side of things, and today, wait, what do you see now? The presentation.
We see Earth velocity model.
Yeah, but is it like Okay, now it's black, yeah?
Y-
Okay.
Yeah, it was black and it
Okay.
has turned to white again.
Okay, so yeah, because I have two screens, it's a bit confusing. Anyway, so the goal yesterday was just to explain the mathematical parts of, you know, the inverse problem, which is important in the end. Most of the time also you use already available codes like we plan to do today. So, but then it's good to know how the things are done. So that's what we spent yesterday for. And today it's mostly how you get a velocity model from your seismic data. So we've already recorded the waveforms, let's say. So how do we go about retrieving the velocity structure? You remember yesterday I mentioned about parameterization when we were talking about the travel time, forward models, and everything. So wait, let me move this. Yeah. Okay. So let's say you have a velocity, you have an F structure. Wait, is it annotated? Oh, wait, sorry. I'm having problems today with my. Do you see the mark?
Yes.
Yes, yes.
A blue mark.
Okay, wait. It's better I just let me stop sharing again and come back. I think I'll just use one screen because this is confusing me. Okay. So now I share the screen. Okay, now it's only one screen. Okay. Okay, great. So let's say we have a velocity structure and we want to parameterize it. Okay, so we need to say give some find the velocity. So okay, we know that the F is in layers. Okay, so we try to in seismology we try to parameterize the F as a layer. So let's say, wait, why am I having difficulties today? Okay, so let's say we have an the Earth. So usually we'll say this is a layer, and we'll call the other half, this part, the half space. So how do we go about, say we have a crust, okay? We know that at least we know the layers of the Earth, the crust, the mantle, we have the core and everything. But the crust is also, you have some other layers, discontinuities in the crust and also in the mantle. And we know that the velocity of the crust increases with depth, okay? So when we want to derive a velocity model, a good practice is to what we call parameterize into different layers, like I'm showing here. And then each layer, like we have here, so we consider here as depth that goes down, and let's say here the velocity, the say horizontal. Okay, so in 3D, it's going to be something like this. Okay, so you have your Earth, and then you try to, this is your depth. This is say X, Y, okay. And so let's say we have a seismic station here. We are trying to find the velocity structure beneath this seismic station, or in 3D, the whole, let's say this is the whole of Trieste. So we want to find the velocity structure beneath Trieste to some depth, say 100 kilometers depth. Or if it's just a shallow experiment, say, I don't know, 5 kilometers or something. How we go about it is to define some layers, okay? And then with each layer, we say we have some k+1 layer. So we define our structure. So we have to choose some maximum depth that we want to go to. And then we define some k+1 homogeneous layers, okay? And we give some, we define some model parameters for these layers. So let's say if we are going to say 100 kilometers, we will use, say, here in this case is 1, 2, 3, 4. Okay, so it will be 4 plus 1 layer, where the fifth layer is the half space. Okay, because we cannot go to, this is the, how do you call it? The half space, okay. And then within this layer, we define the velocity. So here we have the number of layers, the depth to each layer interfaces. So these horizontal lines will be the layer interfaces, okay? And then we define some elastic parameters for each layer. Because we want the velocity is it's some combination of some elastic properties. You remember the definition of P and S wave velocities. So here we define, say, the shear velocity for each layer. Say we call that beta 1, beta 2, beta 3. You can also have, say, alpha 1. It's not shown here. Alpha 2, alpha 3, okay? So that will be also the P wave velocity for each layer. Alpha, say, 4. And we can also, so here, gamma, I think gamma should be, gamma is, I think, this is giving you the VP-VS ratio of each layer. So we know the relationship between VP, VS, you know, I mean, if we consider a Poissonian crust, it's square root of 3, okay? But this is when we consider a Poissonian crust. So we use some, say we use a shear, shear modulus of, say, 0.25 or something, and then we get, but it changes for each layer. So we can define some range. Usually it's between, I think, 1.6 to, say, 1. Or 2.0 for some crust, for the crust, and between, say, 1.6 and 1.9 for the mantle or something. But the point is, with each layer, we give some model parameters, some parameterization, and it depends on the software you use. Some softwares will ask you to give the VP-VS ratio, and then will only ask for, say, an S velocity ratio, or will ask for a V velocity ratio. Now, if you give a VP-VS ratio, you know that, and I give the X value of the layer, then I can compute the VP associated with the layer, because I just use this relationship. Sometimes you can also, you are asked, some software will ask you for the layer densities, okay? So we can also compute the layer densities, and usually we have some empirical relationship between velocity, seismic velocity, and density. So even if you have only VP, this is just a relationship using VS. There is also a relationship using VP. If you have VP, VS, you can also compute the density of each layer. Then the goal of the inverse problem is that we are going to be searching for the velocities, okay? So we don't know the velocities. We assume, usually we will assume that we will set like a constant VP-VS ratio, which is 3. And so the model parameters we are looking for now will be the layer velocities, okay? But depending on the goal of your project, you can also cast you remember yesterday, we can cast the VP-VS also as an unknown, as a model parameter. And then we have to also search for these things. So different projects requires different parameterization, and this is how you define these things. There are programs, say the program that we will be looking at, let's see, I think, wait, I thought I did this, sorry, this thing wasn't working. Okay, so where is the Zoom again? Share screen, desktop one, yeah. Okay, so let's say with the computer programs in seismology, I think I should increase this. How do I make this bigger? Okay. Okay. Usually this is how you define an Earth model. I mean, there is a lot of the documentations on each software as to how to go about defining this parameterization. So these are some things you, wait, where is this? I want to annotate, okay. These are some things, these are really some writings for each program is different. Probably there won't be anything, but this will be something, say model names and everything. And then you go here, here you define the parameterization actually. So in this case, it's asking for each layers, the depth to each layer, the VP, the VS, the rho, some attenuation parameters and some other parameters that probably you don't need to is fixed, or you don't need to change that much. And so you say this is just a simple layer of, so here it's just the surface, it's a layer of a half space. And so the half space, the thickness of the half space is almost every program it's defined at 0. And then the first layer, what it means is that the first layer is 40 kilometers, okay? And then its VP is given, if its VS is given, and its rho is given. So these are how you define the parameterization. And then the goal is to say, oh, did I close that? Okay, so then let's say you give, like I just showed you, you give an initial
question.
Hello?
Yeah, hi. I have a question.
Yeah, sure.
The layers, please, did you count it from down, or it was from like up or down?
In this case, it's from up to down.
Okay.
So so it says we define the Earth model as a stack of n+1 layers, okay, homogeneous, whatever.
Okay.
So you say the first layer, I say 1, 2, 3, 4, okay, or to the kth layer. So in this case, let's say it's 4, and then this will be the last one. This will be the 5, but we are interested in just the k, okay, the first k. So it's k+1, so it's 1, 2, 3, 4. So k is 4. And then the last one will be the half space. So in this case, it's only 1 and 2. Okay, so it's k+1. Remember k+1. So the answer is, say here is 2. So it means k is what? 1. So it's just one layer, and the next one is the half space. Okay?
Okay, thank you.
Yeah, so that's how you do the parameterization. And then now what we're interested in is just then to say retrieve these model parameters, which is the velocities. Okay, so how we do that is what we're going to go through today. Yeah, I was planning for a more interactive section, but it seems, unfortunately, I mean, it's also my fault. I should have asked you to install this project, this program some long time ago. Anyway, so I think we start with, let's see. Okay, so on the, no, I cannot even change the, okay, so I should do this before. Okay, so on, okay, I'm not annotating, so probably. So on this project, this codes project site, there's a lot of tutorials. Maybe some of them you've done in classes that you might want to look at. Some might you haven't really probably done yet, but the point is you can do a lot of things here. So there is some synthetic tests related to source and moment tensor inversions. There is surface wave analysis, there is receiver functions, and there is a structure. We'll go through it. There is a source and seismic data instrumentation and velocity models and everything. So you can go through everything. I think we will start with, okay, let's start with surface waves. Okay, so I'm going to just put, so I mean from we start surface waves, you already done the theories and everything. So there's group velocities and phase velocities, right?
Yeah. Yes.
Yeah.
Okay.
Yes, yes.
Yeah, so the properties of the main properties of the surface waves are the dispersions, so we can use these because the velocity of each at each period increases with depth. We can use this dispersion information to investigate, say, the lithosphere. Okay, so it says this lesson creates some synthetic seismogram by surface wave model superposition. Okay, so we're interested in group velocities. Okay, just to go through the whole thing, I think you can read this later. So it's just I mean, once you install the program, you can come here, you download this lesson A. Okay, you read through it. It gives you everything that you need to do. So you download the lesson A, you unpack it, and there's a README, there's a do it, which does everything that I'm just going to show, and then clean the light to clean the directory and everything. And in this case, so what we're going to do is to kind of synthetically generate a seismogram assuming some fault model, okay, where we can define the fault model by the strike, rake, and dip. So these are the three angles, or the displacement and something, and the normal to the fault. You can use that to also define the fault geometry. So we define the fault geometry as this, and we use this to generate some Rayleigh wave signals. And then so once you have the surface wave, you want to pick the dispersion curves. So that's what that contains the velocity information. And this program will give you some graphical user interfaces, so you can check. Okay, probably we just have to do it, and I don't know, do it and explain. And okay, let me just run the code, and then we can, let's see where it is. It was here, day 2, surface waves exercises. So okay, so lesson A. So we have these 3 things. So okay, let me just open it. Let's see what it is, and let's read through it. So of course, you have to read through the codes you're running, so at least you know what it is, but we cannot read through everything. So there is a cleanup, something that cleans up. Let's say if you've already run this cleanup before. Here it says it creates a velocity model interactively, so here it's the same thing. So once you look at the documentation, you get a good idea of how to create these models. So like we saw in the file that I showed you, this is just a 1 layer over half space with some velocities and VPs, VS given, and the densities in gram centimeter cube in this case. Sometimes some programs will give the densities in kilogram meter cube, so you have to be careful and you have to change it accordingly. And then it creates some files, and so this part does the surface wave analysis, synthetic generation, using some, I think this is H, will be some source depth or something, and receiver depth. So the source will be at 10 kilometers, and the receiver, of course, it says on the surface. So it does that, and these are where you define the focal mechanism parameters and everything. And so do interactively the analysis, which we're going to do. So it uses a program, do MFC, that does the dispersion frequency time analysis. So we'll see how, and then there is some plotting And yeah, okay. So let's close.
Oh, please.
Yeah, sure. Go ahead.
Where we had the receiver position.
Here.
So before you maybe use the code, you have to know the receiver position. So if maybe you don't know the I'm sorry, not the receiver, the source. The source. You have to know the source. So if you don't know where the distance, where the source is, like how would you get it? Like
no, so this is just a synthetic test that we assume some source. Now let's say if an earthquake happens, there is a huge amount of data about this, and even if you can use the inverse problems. I know yesterday I sent you some the document I sent you. We're supposed to do some exercises that you can also use the inverse techniques to constrain the depth of your earthquake. Okay.
Okay.
So that information, it's available. If it's not, you have to then use other techniques to get that information.
Put it in. Okay.
Okay. So the source depth is usually known, and so this is it's not really much of a problem. Okay. I mean, it's just same as knowing the source location and distance and everything. Okay. Because if you know the distance of the earthquake from your station, then definitely that information will come in addition with the depth information.
Okay. Thank you.
Okay. So yeah, we have this available, and then this is just README. I think it's important to just look at it. So it's lesson that creates synthetic seismogram by surface with the whole thing that I just read. Okay, and this is a very interactive, very simple thing. So once you have these programs, you can, I know it asks you to check some. So say do MFT, you can check if you have the do MFT just by, so, I have installed it. It's called programs 3330. So I have the do MFT, everything. So I just go ahead and just run the do it. Okay, so it does, in the background, it does this computation of the, say the forward computation of generating seismic waves, okay, and then the propagation. And because you know the location of your earthquake and your station, so it does this forward computation of generating this seismic waveform that you record at this station, and then it gives you. So we have three components. You have the up and down. So the vertical, the north, south, east, west. But in this case, usually if you see, I don't know, I think you discussed this probably last week, the R is the radial component. So we've rotated, and the T is the transverse. We call them the radial and transverse. What it means is that we've rotated the north, south into the radial direction, and then the east, west into a transverse direction, okay, along the wave fronts. So we can go ahead. Now, if we click on this, it gives us some other, I don't know if I have to make this, no, it doesn't help. Okay, so let me just hide this on the background. So once you click on return. Okay, let me just do this. So it gives you some units. So the units of your measurement, I think it's centimeter seconds. And this is the station name. So these are some, because this is a graphical user interfaces, it gives you some information. So station location, you can find your station location. I think event longitude, event latitudes. This is the azimuth, and this is the back azimuth. These are important information. This is the sampling time, so DT. This is the distance, okay, and this is the great circle distance. And this is the number of points in the data and some other information, origin time, everything. So these are all contained in your in your signal. Let's say if you download I think you did something about downloading signals, I don't know, last week. If you download a waveform, it comes with some metadata, okay? And this metadata contains the depth, the location, and everything, okay? So you have this information. So the program picks it up, and you just have to set the unit in this case, and then you go to do MFT. And now it gives you some other choices. You have to make some other choices. Say this is the minimum period you want to investigate. This is the maximum period. This is the alpha. This parameter is related to the distance and I think the frequency cutoff. There is something that you have to read. And then this is just some shading. This is some graphics. And then the most important thing is here, also here, the type. So it shows what type of waveform you want to pick the dispersion curve for. And remember, we chose the Z component, okay? And if you remember the Z component, it has the P and XV, okay? You remember when you did the theoretical seismology that the displacement has the Z component has a part is by the V. You have the V, sorry, the SV component. Oh, sorry, the SV wave and the P wave makes up the Z component, because the UX and UZ part of the displacement is just a combination of these the potentials of the P and the XV. So once you have the Z component and the surface wave, the Rayleigh wave is just a interaction of the P and the SV. So the Z component you have on it the Rayleigh wave. So you have to choose a Rayleigh wave. But if you choose, say, the transverse component, then in that case, it's only made up of the SH potential. So then that one you have to pick a Love wave. So these are some things you just have to note down. And this is the minimum velocity. Okay, this is the maximum velocity. So these are, remember, some bounds that you just set for the program. And this is period what you want to investigate and everything, some other plotting parameters. So let's go ahead and choose here. The alpha, there is options for you to choose, and one of the options you just click it and it changes it. Maximum period, it gives you in the tens, in the ones, hundreds. So let's say if you click on the tens, then this is up to 95. Okay, so then the maximum period will be up to 95. Once you set these parameters, then you just go ahead and say do MFT. And in this case, it gives you this. I think, how did I stand it before? Okay, so it brings you to this screen, and then this part will be the amplitude. Okay, this is then the dispersion curve. So this is the period against the velocities. So remember, these are Rayleigh wave velocities. So it's just a fraction of the shear wave velocity, and it's tried to solve the equations and gives you the relationship between the period and the velocity. So to then pick your dispersion curve, you go to, say, there is the zoom, where you can zoom in. So these are just some graphical things, zoom on zoom mode. So we have in surface wave, we have the fundamental modes, we have the first, second, higher mode. So depending on which mode you want to pick, you select. Usually the fundamental mode is the easiest to deal with. And also it's the one that you can investigate to greater periods, because the higher modes cut off at some periods. They have some cutoff at some periods. So usually we investigate with the fundamental mode. And then this is just, if I want to pick the dispersion curve, I just click on this. So now if I click on this, like I'm assigning my dispersion curves. So, I mean, you have an idea of how the dispersion curve looks like. So these are the dispersion curve, but this is very tiring to just click on each dot, because I can pick these dots also, but these are wrong solutions. So I have to pick which ones I believe are the correct dispersion curves. But doing this it's very tiring. So there is an automatic pick that it kind of gives you like a band, so I can select a huge amount of them at the same time. And yeah, so then I'll say this is the dispersion curve. So I mean, you can define up to where you think the solutions are correct. And let's say if I define in this area, so this will be my dispersion curve, and this is the associated amplitude. And remember also the fundamental mode has the maximum amplitude. So then this helps you to really define the fundamental mode correctly. Say if I should pick something in this area, you see here, it's related. I don't know if you can see this correctly. It's related to this part. You see now this part is highlighted. So you know that you are probably picking some higher mode. So that's not correct. I mean, if you are interested in picking the fundamental mode, so we take this off. And then once I'm done picking the dispersion curve, I'll go to exit. I save it, save as, it saves as the name. And then I can go now, let's just jump to the transverse component. Now the parameters that I set is already there. I go to do MFT, but it's still here. The type is Rayleigh wave, and so I have to change to Lav wave because I'm dealing with the transverse component. So the Lav wave is prominent there. And then again, I go to do MFT, and I can do the same thing. So I pick now auto. So I say automatic picking immediately goes to the fundamental mode, and then I can pick this up. Okay, so this is the Lav wave dispersion curve for this event in station. And is it okay? And then the last one. Also, again, I have to change to the Rayleigh because the transverse component has a Rayleigh wave, and then I pick this up. So these are the things you have to do. You have to practice with these things. And the good thing is you can change the event parameters and get different looking size, different looking dispersion curves and try to investigate. So once I finish picking up, I think the program just goes on. So it gives me my dispersion curve plotted against the theoretical ones. So I think it's showing here. So we did this. We picked that, and then these are the comparison with theory. So I think this is the Rayleigh wave comparison that is here, and then the Lav wave. So it will compare. So you can see what. So in this case, you can see he picked the fundamental mode and he picked the first higher mode also. Okay, and so then if you can really define the higher modes, it's good because it gives you a very good constraint, at least for the shallow part of the velocity structure, because it's mostly the fundamental modes are present in the lower periods, and lower periods are most sensitive in the shallow part of the crust. So it's good if you see them, you pick them, but most of the time it's difficult to really pin them down what exactly is the higher mode. So just the fundamental modes are also okay. And this is the plot of the Rayleigh wave one. And then, so this is it. So once you have, these are the investigation. I mean, this code is just doing everything for us, just also we see what we're talking about. So once we have this dispersion curve, once we pick the dispersion curves, now this becomes our data, okay? And now we try to use that data to retrieve the model parameters. That's the velocity of the structure. Oh, no, shouldn't have gone. Okay, I just will go here and explain. Okay, so we have some velocity model and some dispersion curves, and we try to retrieve, to use this to constrain the earth model, so the parameterization of the earth model. So in the end, if we do the inverse problem, then this is what we call an initial model. So let's say we give some initial model. You remember yesterday we were talking about some prior model parameters. So we give some initial model, and then we ask the inverse problem to change this initial model to give us the better solution to the final model parameters. So then this will be our current or the final one. So we start with here in this case, the blue line indicates we assume that our Earth is made of a uniform velocity structure, okay, to start with, which here is around 4, sorry, I don't know, myself, I cannot see, you have to it's around 4.5. And then we also, so the crustal velocities, even at say 2 kilometers is at around 4.5. This is definitely wrong, but yes, we want to start with a high velocity model so the inversion doesn't get trapped in low velocities. If you read about these things, there is a problem with inversions. If you start your initial model have some low velocities, then usually the inversion will get trapped with low velocities. So you usually start with some overestimate of the velocity, and then the inverse problem try to fit a good velocity model to the data. So then this will be our final velocity structure, okay? And then we can say, okay, so this our velocity at shallow depth is less than say 2 kilometers per second. And then there is a decrease, and then there is an increase, you know, so there is an inversion here, like it decreases at around between 2 to 10 kilometers, and then it starts to increase with depth. Okay, this is how you explain your velocity structures. And these are some other data that you use to investigate how well your inversion has done. So then in the, I think, yeah, okay. Then you can compare your initial model, so he gave, you know, you remember we gave in the, where is this again? Yeah, so look at all the thing it generated. I wanted to show you this. Here, this is our starting model, okay? We just gave a one layer over our space. So we just gave a layer up to 40 kilometers per second as our initial model. And depending on the data we had, the inverse problem is saying, no, this is not that, our velocity structure is not that simple. Up to 10 kilometers, the velocity is around 3.5. So it's almost the same as our initial guess. But then at 10 kilometers, the velocity decreases to say 3.4. Up to 20 kilometers, then it increases. And sorry. And then it increases again, then it keeps increasing with depth. And at 40 kilometers, okay, there is also a jump, but not as big as we thought. And then, but it's still under 4.4, so it's at 4.2, and so on and so forth. Then usually most of the time we can use, it's difficult with surface waves to constrain the layer interfaces, but then what it means is that there is a discontinuity here, there is a discontinuity here, there is another discontinuity here, okay? So then we can find the discontinuities in the structure, but sometimes you have to be careful with surface waves because it really doesn't constrain the interfaces well. What does a better job is the receiver functions that we'll look at next. Okay, so this is the good velocity investigations. And the next one that you can look at is also phase velocities. So also this is lesson B. So we generate some phase velocities and we pick the phase velocities. I think it's giving the same fault parameters, fault model parameters. So we go ahead and do it, and then I explain as it goes by. Okay, so, and then there are some outputs. You can also investigate these outputs and everything. So lesson B, oh, sorry. So you just run to do it because it's already compiled. Okay. So in this case, it generates some earthquakes and picking phase. So the point is, in terms of actual analysis, picking group velocities or investigating group velocities are much more simpler than getting the phase velocity dispersion curves, mainly because there is a 2 pi. If you look at the equations, there is a 2 pi phase change. So there is always, we don't know this, so getting like using just one station to retrieve the phase velocities is really difficult. So most of the time you have to use some network of stations to account for this 2 pi and also the phase of the earthquake. So there is a phase of the earthquake that we don't know which phase is it. So it's quite difficult. I mean, but we still can do it once we have a lot of stations or some other techniques that once you're interested in surface wave analysis, you can see. So here, what you do is it generates the code generates it generates the earthquake for sure. It generates some synthetic seismograms recorded at these different stations. Okay, so here it shows you you pick only the Z for all the stations. So we go ahead and select all, and we go to do PROM. So this is what does the phase velocity analysis. And because again, the Z component, so we choose the lab wave. Then these parameters you investigate, you can read about them. This is I think this is the number of points, period, as this log, if you want it to be plug in log or linear plot, okay, maximum periods and everything. So it's almost the same thing. And we go here, and then this gives us the phase, these are the phase curves. So here we have a lot of different phase curves. Now the possible solution is the one that has the maximum amplitude. So this shading gives you the amplitude scale, and these other curves. I mean, so first we use a lot of stations to get rid of the phase of the earthquake signal. Okay, so when the earthquake generated, the first pulse it has its own phase. We don't know this, so we use a lot of stations to remove this from the equations. But then there's also this 2 pi and ambiguity with the phase because of the periodicity that causes all these branches. Okay, so but usually the correct ones will be the one with the maximum period, so it's easy to see that. And then so again we pick automatic pick the fundamental one, and so we do our analysis. So we say, okay, this is the phase velocity, and then we pick this up. Okay, different programs have a way of presenting the solution. So you have to also, I mean, it's always you have to read the manuals. And so you save it, and then you go to, I think, next or quit. Okay. Yeah, so, and then quit, and then it will bring you the transverse. Now it will bring you the transverse components. So it shows you the peaks. And then I think, yeah, the transverse components, we select all again. We do the same thing. Now it's unknown, this lab wave. We change this number of points to 250. You have to play with this and see what each of these different parameters will do. to how your analysis will look like. And then this, so again, we pick the love wave dispersion curve. And then this is how you do. Okay. And then I think you quit. And then that's, I think, yeah. And then it compares your dispersion curve picked with the theory. This is for love wave comparison. And then the Rayleigh wave. So you read through this. I mean, usually you don't really know what is the theoretical one. So usually you have to just try to, it's just some simple curve, because this theoretical one is coming from some forward parameters that you give to the program. Okay, so it's not really the correct one, but okay, it's good for comparison. And then this is it for this part. So this is how you pick your surface waves with this program. And then, so this is surface wave analysis. You can do the other one. And this is receiver functions. But I guess do you have an idea what receiver functions are? Where is it Zoom? Hello? Yeah?
Yeah, sort of.
Okay, and the diploma students?
Yeah,
Come on,
yeah.
guys, I'm asking, I know how to go about this. No? Okay, I guess. So let's see, I think I anticipated this. So then let me just do a quick recap of receiver functions, so you know. So the point is we are trying to investigate these structures, the velocity model, these velocity models. So this is just a quick introduction to receiver functions method. I think it's just a PDF from Frederick from GFZ. So let me go to presentation mode and okay. So in some outline just so, okay. So the point is we want to investigate the subsurface structure, okay? And if you have money or you are some oil company, you use some reflection seismology, you know, which obviously is very expensive because you have to use some air guns or some explosives and everything. But we can also use the earthquake source, as we know. And so in this case, it helps using these earthquakes and as the source of the seismic waves, we can investigate even much more deeper structures, okay? And this is just the Moho depth and PVS ratio. So why we are interested in the VPVS ratio is that it gives an idea of which lithology it's there in your subsurface structure. And also we know the importance of getting the Moho depth because it also helps us to constrain well the seismogenic zone, because, you know, at least for continental structures, if you exclude subduction zones, the seismogenic zones is within the crust. So once you know that the depth to your crust, you have an idea of where the earthquakes, the maximum depth your earthquakes can come from. So these are some things we need to investigate. And so mostly it's just boundaries and velocities, you know, discontinuities and velocities. And using the surface wave is one part, using also PNS wave, body wave tomography is also another part. But we can also make use of this, just the idea of reflection seismology, okay? So you remember in reflection seismology, oh no, that's not what I wanted to do. Okay, I annotate. You have a wave that generates and bounce off the interfaces, and then bounce off the interfaces, and it's being recorded by a receiver. So then you have an idea, you can map the discontinuities and everything. So this is what the receiver functions is really powerful for, to map the discontinuities. And how it's done is we use the idea of P and S waves. Okay, so okay, P and S waves, we know P and S wave velocities. So the main point here is that if you like I was saying, the seismogram, the displacements you record, you know, it's a vector field. So the U, X, U, V, U, Y. This is a combination of the P, SV potential. This is also a combination of the USV potential. I think, I don't know, it's plus or minus, I don't know. I don't remember. But, and this is the combination of the SH potential, okay? So if from the theory, if there is a horizontal interface, and I'm going to just, okay, let's just take it from the, okay, let me just do it from up. It's much more simple. So let's say if there is a P plane wave coming, okay, so this is the ray. If you have a P wave coming incident on a discontinuity, then part of it is going to be reflected, part is going to be transmitted. Okay, so let's define some elastic parameters. And so this is reflected P. I think this is transmitted. Okay, this is incident. But because the response of P, it's the displacement caused by P is a combination of X and X, the SV and the P, the discontinuity, how do you call it? The discontinuity at the boundary, requires that there is also an SV wave that is generated. Okay. Okay, the requirement that the displacement should be continuous, that's what I wanted to say. The requirement that the displacement should be continuous at the interface, at the boundary, requires that there is also an SV wave that is generated at this boundary. So an incident P will generate a reflected P and a reflected SV, okay, and then a transmitted P and a transmitted SV. Okay, same also goes for an SV wave. So if you have an SV wave coming in, then the requirement that the displacement be continuous will generate an SV, a reflected SV, and a reflected P. Okay, and you remember why the P is much more away from the normal, because the velocity of the P is greater than the SV. So SV is closer to the normal than the P. Okay, and so this is the idea of receiver function. So let's say we have our, I don't know if it's explained better somewhere. Okay, I think I'll use this slide. Oh no, probably. Sorry, let me just go back here. So I'm clearing this up. So let's say we have this is our surface. Okay, this is Z0. We have our receiver here. And we have a discontinuity here, okay? And then there is an incident P coming in. Oh, did I draw it really well? So this is an incident P. This is the discontinuity. Then there is a P that is generated, okay? And then this is so this will be a transmitted one, okay? So now the P is coming from below, and then this will be an SV that is also generated. Now, because this layer will have a P wave velocity that is greater than the S wave velocity, this P will arrive earlier than this X. So we can use the time difference between the arrival of the P and the X to constrain the thickness of this layer, okay? And you can imagine that also if there is another discontinuity here, the same principle will happen. So it will generate a P and an SV, and then another P and an SV. So then it gives you a way of constraining the discontinuities, okay? So this is basically as what receiver functions are about. And if you, then the amplitudes, so okay, let me just go here so we can, okay. So once you do that, then this will be the time, so this will be, say, a direct P, and this will be, and I think this is PS. So this is the PS time. This is the time difference between the direct P arriving and the SPS time difference. And we use this time difference to constrain the layer thickness. Okay, so we can map the discontinuities, and then we'll use the amplitudes to constrain the velocities. Okay, because if you remember the how do you call this? The reflection and transmission coefficient is also it has in it the impedance, contrast, and everything. So we the amplitudes that is reflected or transmitted has an information about the velocities. So then we can use that information to also constrain the velocity of the layers. So this is what a receiver. This is how a receiver function looks like. Okay. So we use it says we use the time separation of the wave converted from P to S to other discontinuities. Okay. And then there's a take home point. So interfaces with velocities increases. Interface with velocity increases with depth shows as positive vehicles and negative. Okay. So what it means is that if we have parameterization and then there is a velocity increase, okay, so velocity increases with depth, then it will show as a positive thing, and if the velocity decreases, it will show as negative wiggle. So these are some things. This is what receiver functions is about. And let me see if there is something more. I mean, I cannot. Okay, so this is P to S. Okay, so now I was just talking about P to S conversion. Okay, so from if you have a homogeneous say layer, like a very flat layer, horizontal layer, then the incident, why did I write two lines? The incident P will only generate a P and an SV. Okay, so if you do the analysis of the receiver functions that we're going to go through, then if it's this thing doesn't generate any SH component, okay, any SH wave. So if you look at the transverse component, there should be no signal, there should be no energy on the S wave component. There should be only energy in the radial component, not the not the transverse, because there is no SH wave coming from the conversion of the P and from the P at the interface. But if you have an inclined or not a horizontal layer, then there is some SH potential energy that is generated. So depending on, we use of this to also have an idea if your interfaces are horizontal or inclined, dipping interfaces. So these are the things you investigate. And yeah, so okay, this is what I was explaining. So this, the P initial incident wave is coming, it converts. So this is, and also there's multiples. So let's say there is this P waveform is coming. Okay, this is just some infinite horizontal layer. So if this when the incident wave impinges on the surface and the interface here, then this is what it means is that this is coming as a P, okay? Then this will reflect, because the station is here. We're just recording beneath the station. So we want the structure just beneath the station. So this P goes, it's converted as a P. So it converts, it travels as another P, then it reflects at this surface. So this is Z0. Okay, but remember, this is also another interface. So there's also a conversion here. Okay, but then this is S, so there is nothing transmitted. So then this comes down as also a P, so there is also another S. And whilst this, it comes as a P, it goes as a, I think it goes as an S or a P. Why? What's the color skill? Okay, I cannot tell. But I think this is a P that goes as an S and comes as a P and then goes as an S again. Okay, so it's a P, P, S, S. So these are some nomenclatures you use, and this one goes as, I think this is just a P wave that is coming in, and then it's converted and it goes as a P. Okay, so these are the things. And with all these multiples, you can see them also on your receiver functions. So this image is not very clear, but this is, I think this is P, S, P, P or something. So all these wiggles will indicate what reflect these multiples or this multiple reflection at the interfaces. And so, yeah. And then we have also so we just looked at the P to S conversion, and we can also have a P, an S to P conversion with the receiver functions. So we can choose which one we want to use. And yeah, I think this is the deconvolution. I just want, if there is another, okay, I think this is what. So how do we go about this receiver functions? It's more of a convolution, deconvolution problem here, because usually your S and your Z, your horizontal and radial component will have the P and S wave, SV potential, so waves. So then the technique for the receiver function is just, I think, yeah, it's just a deconvolution. So we want to take, so this waveform that we record has the source information and also the instrumental effect and everything. But we want to take those things out, and all that we want we are interested in is just this waveform, just this conversion of P to S. So how you do it is to just deconvolve the horizontal component from the radial component, okay? And then this will give you the receiver functions. This is what we call the radial receiver functions. We can do also the same receiver functions for the transverse. That's just a deconvolution of the of the transverse component waveform, the horizontal from the transverse component. Okay, so deconvolution. This we have what is done here is a Fourier transform. So you just you transform the time series into frequency, and then you just then the deconvolution is just a division, you know, because then convolution is a multiplication. So deconvolution is just division. So this is just signal processing. And then once you do this deconvolution, then you get the receiver functions, and yeah, and then you can use that to investigate your structure. So I mean, it's a bit more involved, but this is just the gist of it. You just have to read more about this, and yeah. So if we look at this program also, so this program allows you to do this receiver function analysis. So there is some things here. So, and I think this code is mostly divided into three parts. So this is, I think, event. So you get your event, which is your earthquake, and you do some event processing. Then it's important because you remember the three components are east, west, north, south, and up and down, vertical. And then you do a rotation. So you rotate the north, south into the transverse component, and then you rotate the east, west into the, sorry, you rotate the north, south into the radial component, and east, west into the transverse component. So that's that we'll look at the codes, and then then you you deconvolve it, and then you get the receiver functions. Okay, so once you install the program, you come to this part. I think you download, so the testing, everything is in this this package. You download, you unpack, and then you do these things in so let's see. I think exercises. So okay, so I downloaded it, I unpacked it, it's here. And okay, no, I don't know what's here. Let me just delete this and we do the whole thing. So you do these exercises. Okay, so it's just unzip. I want to see receive functions. Okay, so now it unpacks, and then we can go in here. So it creates for you some seed, and this seed is just a format of storing seismic data, the waveforms, and some metadata. But now it's being obsoleted. So I think the recent formats is mseed or and mini seeds. So that's how you save the waveforms. That's the way to download waveform signals. Okay, so it says that we should go into the SAC directory, and then run this. So this now this RD seed it's a program. It's a program, and there's a package that converts your seed signal to a SAC signal. So SAC is just also another way to solve to store the waveform signal. Okay, it can be I don't know. There are also other formats like mini seed and everything. So I'll just go ahead and run this. So okay, there is nothing in here, and only the seed thing. So I just will run this, and then we can see what. So also there is documentations on this, on what each one of them means. So you have to. Okay, so what it means is now we get our SAC signal. So it converts the mini seed to SAC. We can look at what it is. So these are the waveforms, okay? Then we can read them. So this is the this is the east-west. This is the vertical, and this is the north-south. Okay, so this is the signal. So this is, I'm just reading the east-west component. And then we can plot them, and then you can see your waveforms, you can see your signals. So once we have our signals, our waveforms down, then we have to do we have to run this code now. Let's look at what is in here. So it says run this I-do event. And let's see. So this there's some comments, so you can also know what's doing. So this makes entry into various commands. Okay, so it's setting some event, your earthquake parameters. There's some data, metadata actually. Here the event occurred, demand, I don't know, demand, the day, I think the seconds, the longitude of the event, the depth, the magnitude of the event. Then it makes some directory. So makes some directory good. And then it picks each SAC signal and it sets. So this is, you have to also read the documentation for this, because there is a lot of things. I mean, you get used to this once you work with the data and with the codes. This is setting, I think, the network name, the station name, the location, some data, some delta component. And then here it's setting some, some frequencies. And then this line does, what this line does is the generate some responses of the instrument. So you can do a deconvolution of the instrumental response. Okay, so you remember that the last time we were talking about, is it? No. Sorry, probably not, you guys. Wait, how do I write? Okay, I think I still can write. No, okay, I have to do this. So the waveform that you record is, I think it's a convolution of the source, the medium, okay, and then I think the instrument at this the instrumental response, okay. So the source, it contains information of the source, the medium, and then the instrumental response. So in receiver functions, you want to get rid of the source, okay, because we just want the information of the medium just right beneath the station, and you want to get rid of the instrumental response, okay, so the response of the instrument. So this part of the code, where is it? Okay, this part of the code is what does that, this transfer from so it's a transfer function that removes the instrumental response. So this is what does this part. And then once you remove the instrumental response, so now it's, so if we remove the instrumental response, then our signal is just the convolution of this, the source, and then the medium. Okay, then it saves them, it saves the modified waveforms in the good directory as SAC. Okay, some names and then the SAC. Okay, so let's go ahead and run this. So I think it's just, I do event, so it rotates this, does that, it gives you the results. So now we can go into the good directory, and now this is the, so it just removes the instrumental response and it just saves them here. Okay, we can look at them. I mean, this is also, so we use a program GSAC, and also there is another program that is called SAC actually. So there is a GSAC and then there is SAC you can download. Also, you probably, if you are interested in doing these things, but now there is also Python, OSPy that does all these things. So people have really turned away from SAC anyway. So then we can read the SAC thing, this program, and then we sort up distance. These are just some plotting things just to see the waveforms. Okay, so then these are the waveform. Oops. Okay, so I cannot move when I am here. These are the waveforms. So this is the waveform with the instrumental response removed. Okay, so this is the E component, this is N, this is Z component, and we can see clearly the P wave arrival here. So, and I think this is the S waves, and then the service wave are behind. So we are interested in just the P to S conversion. So this is just reading this part of the data. Okay. So we quit. Okay, and then it adds us to okay, so now it asks us to then do the rotation. So again, let's go ahead and open that up and see what's in here. Okay, so here it says just set some variable destination file. This means destination file, final, some high frequency thing for, I think, for filtering, and then signal strip for processing. Okay, iris data signal. Okay, so this is just, these are just some Unix codes. This is make directory, you know, delete directory and everything. And then this part is, it's not retained. Okay. And then this part where it's a rotate. Okay, so it takes so it takes the waveforms here and it reads them. It's, I think this is remove the trend, and then this does high pass, a high pass filter using this cutoff frequency. And yeah, so this part is just a filtering part. So you filter the data and you save them in temporary file. You don't overwrite your original data, else when something goes wrong, then you lose everything again. And then this part, okay, then you just create some directory, you save some names, and yeah. And then here it does the rotation. So you read the data, so you read the H, Z, and E, and then it does the rotation. I mean, so you rotate the horizontal components. So we call the horizontal components the north and the north, south, and east, west. Those are the horizontal ones, and then we rotate them. The code does through the rotation, and then it saves the file, the name of the files, and then what it does again. If we don't have the horizontals, okay, yeah. So if we don't have the horizontals, then it does something else, because we don't rotate the vertical component. So we are only rotating the horizontal component. So this is just, I think these two parts just take care of some different components. So it's just the same thing. So this code just does the rotation. And actually, it's quite straightforward once you have this program. So which one was it? No, okay, this one. So I'll just go ahead and do that. I do rotate. Okay, so it does a rotation, and then it asks you to go to the final directory. So now, each step it creates some new directories with just the Linux commands, and then, so that's not really processing, that's just file keeping. Okay, so these are the rotated components. We can again read them and plot. Oh, please tell me where you plotted. Yeah, so now you see the names have been changed to R, so BHR. So this is the radial component, this is the transverse, and this is still the vertical component, okay? So now, once we have done this, then we can now do the deconvolution, okay? Now, the deconvolution in receiver functions, if you're interested, there are a lot of methods to do the deconvolution, because it's not really, how do you call it, unique. The solutions are not really unique, especially if you have noises on in your data. So why? Because of also the you remember when I just showed you the equation, it's the R, okay, in the frequency domain, it's a division by the Z. So if there is a zero value here, then it's undefined, okay? So it's quite a tricky process. So sometimes you have to shoot all these values up, what we call the water level, so that there is no zero. And some other methods, some depending on which deconvolution you use, like yesterday, the inverse problems, your solution is a bit different, but in reality, it shouldn't be that off. But sometimes it can be really, really bad, especially depending on the amount of noise you have to use. So when you are doing some work with receiver functions, sometimes you might want to play along, play with some different convolution methods. But like, let's say a program like this, it's really well tested, and the results are often really good. Okay, so we go ahead and say, okay, we've done this, and then this is the receiver function component. Okay, so now we just go and do the receiver function. So we do receiver functions. I think you go to the main directory, okay, and then we run this program. Now let's see what this is. So so this prepares the receiver functions. So this makes the receiver functions, and Okay, these are just Linux commands to create some directory. So create a receiver function directory, time before, time after. Time before, time after is, yeah, you remember when we saw the image of the receiver functions is something like this. Whatever. Okay, sorry, it's really bad. Okay, this is the time before. So time before the zero peak. So okay, so you want some time before, and then time after the first, the peak of the p. So how long you want to investigate your time series should be. So that's this that, and then okay, current directory final z. This is a case for prototype component name. Okay, because there are different component and BH, HH, and EZ, so different component name depending on which component name you have. I think so. There is no, it's kind of, you don't get any runtime errors. Then you read your in the final directory, you read your Z, your R, and your transverse component. You remove sorry, you remove the trend, you high pass filter. You can change the filter parameters. You plot and you do a picking. So it's an interactive picking. Then you interpolate or desample your data. You synchronize the times. So all the times are the same. So the P doesn't arrive in the Z component before the, let's say before or in the R, in the radial component. So you synchronize the time. And then this is the deconvolution part. So in this code, it uses a time domain iterative deconvolution. And I think this program, this is the program that does this. It's the SAC iterative deconvolution. And the thing is, once you have, where is my project? I don't remember where I saved this. But you once you have the source code, okay, for this program, you can look at this is, I think it's a Fortran code that I have. I mean, once you install the code, it's like the compiling. So you can look at this, the source code of this, and see what it's doing. You can see inside the deconvolution and everything in there. So this is what does the deconvolution, and then it gives you the output, and then you save the output. So in the end, this will be the receiver function. So let's go ahead and run that. So okay, so you just say run do RFT. Okay, so now it asks us to pick the arrival times. Okay, so the P arrival is very prominent always on the vertical component. So I'll pick from the vertical component. You see in the transverse component there is almost no P energy. Okay, there is also some on the radial one. So usually you pick on the P, and because of the time before, time after, you don't have to be precise, but also it's good to be precise. So you can, I mean, if you look at the documentation, you can zoom in and then you can really pick some P. So here, if the zoom in, I click on XX and then it zooms in, and then I'm going to click P for P wave and then Q to quit this interactive. So it picks the P arrival and then I quit it. Then it does the computation. So this is the iterative deconvolution. So it deconvolves the P signal from the radial and transverse component, and then it gives me some statistics of how well the signal was reproduced, and some other number of iterations and everything. Okay, so now it creates the receiver function directory and it puts the resource in there. How do I clear this? Okay, oh, our time is up. Okay, but we're almost done with this part. So this is the receiver function. So this is the R receiver function. This is the radial receiver function. This is the, so let's, again, to look at them, we go to, we use the GSAC. Then we read. So it says, go into the receiver functions, read everything. and then it says file ID, name. So it gives the name of the plot. And okay, let me just plot. Go ahead and do assets axia. Oh, I think I got it wrong. Nah, that's not what I wanted to do. Sorry. I think it's this rather. Okay, so file ID is name, then plot. Why it's not plotting? Right. I think my resource is hiding somewhere. Okay, so then this is the final result. So we saw the signal, and this is the receiver functions computation. So then the point is, okay, wait, probably I can do this now. Okay, so now the point is we can see that this is the radial component and some parameters. So this is what we call the Gaussian, because we use the Gaussian for the iterative deconvolution. So these are some Gaussian parameters. You can this 1.5. Okay, wait, now I can annotate. These are some Gaussian parameters. So this is high frequencies, the alpha, which controls the width of the Gaussian. The bigger it is, then it allows for much more high frequencies. So here, the 2.5 shows a much more like high frequency signals, whilst the 0.5 is very smooth. So these are long period signals. So this is the receiver function. These three are the transverse components. Then these are the radial receiver functions. Then this is the transverse receiver functions. Now remember from the simple introduction, we said that if the layers are horizontal, then there should be no energy on the transverse component receiver functions. Okay, so once you have a bit of energy on there, then it's indication that of course your surfaces, your interfaces are not horizontal, or it's not isotropic as the initial is. So there is some anisotropy that's causing some energy in the transverse receiver functions. Okay, now what's the goal here? Now the goal is to use this as your data and try to find an structure that can reproduce these receiver functions. Okay, so then this is how you retrieve your velocity. So all this is kind of some initial pre-processing. Of course, sometimes in the plottings, I think it's shown here. And the plotting, sometimes so once you do it for a lot of data from different back azimuths, you can have a plot like this, and it gives you an idea of where there are interfaces. Okay, and so you can use just this raw data to make some initial assessment of your surfaces, but like only probably the interfaces. You cannot tell about the velocities and everything. So to get constrain the velocities and the interfaces better, then the point is to model these receiver functions. Okay, and that so you try to retrieve an S structure that can reproduce these receiver functions, and then that S structure that you get will be your velocity model. So this is how you use the receiver functions to do the receiver function, to retrieve the velocity structure. So in the afternoon, we'll do this inverse process of using the receiver functions as input to retrieve the velocity structure. Okay, so what we did here, this section is just a kind of a pre-processing also for the dispersion curves. Yes, once you have your dispersion curve, it can tell you something about the velocities, but you want to actually constrain well the velocities or the model, you need to do an inverse problem. So you have to use the dispersion curves as inputs and try to generate your velocity model also with the receiver functions. Okay, so in the afternoon we look at the inverse problem of generating the F structure from the receiver functions.
Thank
and
you.
the surface wave signal. There is one more thing. Hello?
Yeah, thank you.
Yeah.
Okay. In the meantime,
Thank you.
if you have some time after lunch, you can try to see if you can install the program. Okay.
Okay.
Yeah.
Bye.
Thank you.
Simone.
Yeah.
Yeah,
Oh,
yeah,
yeah. Someone indicated that it's time. Yeah, I'm sorry to go overboard, but just wanted to finish this up. Yeah. Okay. So enjoy your lunch. See you after lunch.
Okay.
You
Okay,
Bye.
thank you.
Simone,
Hey, Jacobo.
how are you?
Hi,
Fine,
Simone.
Good. How was your exam?
It was fine. It was fast.
It was
mean,
fast.
Yeah, it lasts 20 minutes.
You said?
It lasts 20 minutes. In 20 minutes, 25, I've already finished.
Okay.
Yeah.
Okay, nice. Cool.